right, so any questions? Well, basically, the idea we talked about last time was work, meaning foot-pounds are the units we want to end up with. A lot of times the feet is the dx. The only time it really wasn't that was when we were doing the liquid being pumped out of the tank, and I don't think I'm going to put that problem on the quiz, so we don't have to worry so much about that. Because then in that one the dx was part of that was the thickness of the slab. That was part of the volume equation. And there was one of those problems, wasn't there? Wasn't there one of those liquid problems? Okay, so do you want to go through a few of those? Just to review here would be a good plan. What do you think? You guys tell me. Basically, the rope and bucket problems, you basically had to set up an integral with pounds in it. You want to get foot-pounds. So in these two problems, you need to set up the integral with pounds. Well, the spring problem, you just use this little equation right here, K times X, force, whatever the force equation is from Hooke's law. And in the rope and bucket, you just got to add up the pounds. How much does the rope weigh? How much does the water weigh? How much does the bucket weigh? And you just put that in your integral. That's basically it. So Emily, what were you thinking there?
Like A and B. Sometimes I don't know.
On here?
I guess on either, yeah.
Those are typically always going to be feet. So it's how far either the spring is compressed or stretched. You know, from rest would be 0. So the spring at its natural length would be 0.
So whatever X or whatever whatever X is.
Whatever unit that is what unit those would be, right? And so the rope of the bucket, if you're lifting it up, you know, from the bottom 20 feet, 0 to 20, right? Is what that's going to be. Okay, so yeah, which one?
7.
Number 7. So 7 says, is it more work to raise a 60-pound bucket from a 60-foot well or a 50-pound bucket from a 70-foot well? Assume the rope weighs 0.25 pounds per foot. So and we're not talking about any water in the bucket. It's just the weight of the bucket. So we're going to have, if you've got a 60-foot well, so we're going to raise this. This would be 0. This would be 60, right? So what we said then is that, okay, let's say the bucket is right here, right? So we'll call that X, right? So this length right here is 60 minus X, right? So that's how much rope is out, right? So there's 2 ways we said you could do this. So how much does the bucket weigh? The bucket weighs 60 pounds. So it's going to be 60 plus, and then we got to do the weight of the rope. And the dx is going to be the feet, right? So this is the feet. Because we're talking about, the reason the dx is a feet, remember, dx is that little tiny part. So we raise it up a little bit, and a little bit, then a little bit, and each time we pull it up, the rope's weighing less and less, right? So that's why the dx is the feet. So this is going to be pounds, and then how much is the rope? Well, we said there's 2 ways to do it. One is just look at it this way and say, okay, when the bucket's right here, how much rope is out? Well, it's 60 minus X feet times what? 0.25 pounds per foot, right? So that's how many pounds of rope there's going to be. So you can just put in 0.25 and then 60 minus X. Okay, that's one way to do it. The other way we said to do it is make yourself a little table. Okay, so now to be honest, that's almost harder in this one, because if it's 0.25 pounds per foot, how much does the whole rope weigh? How would you get that? 60 times 0.25, right? And what is 60 times a fourth? 15. So this rope weighs 15 pounds. So when there's 0 feet of rope pulled up, it weighs 15 pounds, right? And then what would be the other point? 60 and 0, right? When there's 60 feet of rope, remember this is feet and this is pounds, right? So when there's so a lot of times the problem might have been, it might have just said the rope weighs 15 pounds, right? If it just said the rope weighs 15 pounds, then this would have been an easier way to do it, right? But, or you could have divided. You could have said, okay, 15 divided by 60 is 0.25. So either way. So what we said is, okay, now you can take these 2 points, do your slope calculation. So 15 minus 0 0 minus 60, and so that becomes negative 1/4. So there's my slope, and so you could have wrote your equation, y equals negative 1/4, and then, well, let's just use that. That's your y-intercept. So it'd be x plus 15. So right here we could have put negative 1/4 x plus 15. Well, if you look at those two, they're the same thing, right? If you take that times that, that's 15. That times that, that's negative 1/4. So you get the same thing, okay? So either going to do your, so for the rope that's changing, either do that or do that. It doesn't matter. And then, Emily, the integral would go from what to what?
Wait, 60 is 0.
Yeah.
So 0 is 60.
That's right. So we're pulling this up from 0 up to 60. Okay, now, they said, now, here's why they asked this question. So in physics class, it's just foot-pounds, right? It's just force times distance. So in physics class, you would say, okay, a 60-pound bucket, so it's a heavier bucket, but we're not pulling it as far, right? So a 60-pound bucket in a 60-foot well, you take 60 times 60, that'd be 3,600, right? 50-pound bucket, lighter bucket, but we're pulling it farther. 50-pound times 70-foot well would be 3,500, right? So the 60-foot bucket, or the 60-pound bucket in a 60-foot well would take more work to pull up, right? But than the 50-pound bucket. But in the 50-pound bucket in the 70-foot well, you got more rope, right? So if we don't ignore the rope, in physics class, you would ignore the rope. If we don't ignore the rope, that might make a difference. That's the idea here, okay? So now in this one, what's it going to be? Well, it's going to be a 50-pound bucket plus, and then we do all the same stuff, right? So it's 0.25. This time it'd be 70 minus x. Or we would say 0, 15, and then we would, oh no, it wouldn't be 15 this time, would it? Because it's 70 feet, right? So it'd be 70 feet. So then you'd have a different number there, right? So I'll just use this and keep it there. But you'd have 0 and 17.5, right? If it's 70 feet, a fourth of that would be 17.5. And then when it goes all the way to 70, it'd be 0. So you do your slope calculation. Again, it'd be negative 1/4 plus 17.5. Same thing. Okay? And then this time it'd go from 0 to 70. Okay, so what'd you get when you type those two? We get 4,050 for the top one, and 4,112.5 foot-pounds. Okay, so this one, if you ignore the rope, would have been 3,600, and this one would have been 3,500, right? So this one would have taken more work than this one, but because of the rope, and there's more of it in this one down here, it ends up offsetting that, and ends up actually being more work to do. Okay, so that's a good one. All right, what else? So definitely want to be able to do that, a rope and a bucket. Well, let's try this spring one right here, just for practice, right? Okay, you guys set that one up right there. This would be what you would normally hear me ask in a spring problem. So if we can do a rope and a bucket, we can do a spring problem. We're good. So what's the K value? 5 halves, 2.5. So the force equation, Hooke's law says force equals K times X. So force is the pounds, and it takes 5 pounds to move it 2 inches, right? So K is 5 halves or 2.5. So your force equation is 2.5x dx, and it goes from 2 to 4. That's all there is to it. Well, what's the natural length? Remember I said earlier, the natural length is 0. The natural length is 0, right? So what's the natural length of the spring? What's it say up there? What's the natural length of the spring?
6 inches.
6 inches. So here's a wall, the spring is attached, and it's just sitting there 6 inches. Okay, so there's 6 inches. We pull it out to 8 inches, right? So now that was 2, right? So that's 0 to 2 right there, right? But we're going to pull it from there, so it takes some force to do that. And we're going to pull it from there, we're going to pull it 2 more inches. We're going to pull it to 10 inches, right? So this is 0, this is 2, this is 4, right? So the natural length, that's your 0 right there. So from 8 inches to 10 inches, it means we're going to do it from 2 to 4, okay? So it's been stretched 2 already, and we're going to go 2 more. Okay? If it would have been 6 to 8, this would have been 0 to 2, right? 10 to 12, that'd be 4 to 6, whatever. Okay? That's it. That's it. That's all you need. Okay? Any spring problem, you're always going to have to be given some information about K. They'll either tell you K outright, tell you the force equation, or more likely they'll say, okay, this is how many pounds it takes to move it, you know, at a certain distance from its natural length. And then from there you'll be able to get it. Okay? All right. So that's the idea of work. So now let's see, what was the next thing I wanted to do? Okay, let's pull out the 2011. No, wait, let's pull out your 2016 packet. Let's do the 2016 packet, and let's look at number 5. All right, so did we do any of this yet? I don't think we had. Okay, so this was in last year's AP test. Okay, so this was a little different. This was a little bit unusual of a problem, you might say, from many years. The inside of a funnel of height 10 has circular cross sections, right? Circular slices, and they show them. At height h, the radius of the funnel, so at a certain height, the radius of the funnel is given by this equation right here. Okay, where h goes from 0 to 10. They said that this funnel is 10 inches tall. Okay, the units of r and h are in inches. All right, so find the average value of the radius of the funnel. Write down what you think you would set up to do that. Find the average value of the radius of the funnel. And then go ahead and type in your calculator. This is not a calculator. This is not a calculator. Okay. All right. Well, if you don't have it already, you don't know it probably. What do you do for average value of the radius of the funnel?
Put in 10. The h.
partial. That last thing you said is good. The last thing you said is good. The average value of a function f is the integral of the function f divided by b minus a, right? So the 10 minus 0 you got right. But up here, you should have had this. That's it. Easy peasy. Now, you do have to do some work here, right? Average value of a function, right? We got average, we use two different ways. Average rate of change. Now, you were thinking average rate of change. Average rate of change of a function, you put in the endpoints divided by 10 minus 0, right? That slope between 2 points. So if they wanted the average rate of change of the radius, then you'd have been right. You'd have put in a 10, put in a 0, subtracted those, and done 10 minus 0. Okay, but this is the average value of the radius. So it's this. Okay, so what does that mean? Well, the 1/20th, oh, actually this is pretty easy. We can take the 1/20th out front, and then we have 0 to 10, and we have 3 plus h squared dh. And so we're going to just do the antiderivative. So the 1/20th is hanging out there. That'd be 3h plus 1/3 h cubed. Is that right? And then all that from 0 to 10. So we're going to put a 10 in there. That'd be 300. This would be 3,000. I'm sorry. 1,000 divided by 3. So this would be 1/20th. This would be 3 times 10 is 30. I'm sorry, not 300. 3 times 10 is 30. Plus 1,000 over 3, right? Minus, and then we put 0 in there, that's just going to be 0, right? Now, again, do you have to simplify this? You do not. So, I would leave my answer just like that. Now, what I forget? Divide by 10. Divide all that by 10. Right? Now, I could bring this 1/20th, I could bring that 20 down below with that 10 and get 200. So I'd have 30 plus 1,000 over 3. I mean, there's a lot of little things I could do to simplify this, but I wouldn't need to. Wouldn't need to do any of those. Right? Could do that. Right? And there's things I could do. But I can't forget to divide by 10. Okay, now, let me look at, I do have the answers to this. Look real quick. I think I have scoring guide. What number is this? 5? So 1 over 200, 30 plus 1,000 over 3, then they went ahead and reduced that, but you don't really have to. So what do you got? You got 1 point for doing the integral setup right, 1 for doing the antiderivative right, and then 1 for your answer. Okay? All right, good stuff. Now, what about the next one? Find the volume of the funnel. Find the volume of the funnel. Hint, hint, hint. The inside of a funnel of height 10 inches has circular cross sections. Find volume of the funnel. Now, just set up the interval. Don't work it out. Okay, you should have it. What do you got? Oops. What do you got? Easy, easy, right? How do we do? Volume of slices. It's a lemon, right? It's a lemon. The lemon had circle slices. What's the formula for circle slices? Pi times the radius squared, right? To be honest, you could have just put r squared there, right? And then dh. And then 0 to 10, right? That's all it is. Now, why was that easy? Why was that easier than all the volume ones we did? What didn't we have to do in all those that we had to do in all those other ones? We had to figure out what R was, right? And the ones we usually do, when we do them, typically, and I love this question, to be honest with you, because it really makes to see if you understand the concept. What we've been doing is we said, okay, take a region, revolve it around an axis. So this slice right here, this strip, when you revolve it, it's going to create this slice, right? It's going to be a circle slice. And we got to figure out what the radius of that slice is. Oh, it'll be this y value minus this y value. That'll be r equals and da-da-da-da-da. Right? Well, they gave us that. They did all that for us. Right? They did all that for us. So we don't have to worry about it. We don't have to worry about it. What they told us in this problem, they said, hey, here's a volume. Here's a three-dimensional thing that has circle slices, and we're telling you the equation of the radius. Okay, we had to build, in the problems we've been doing, we had to build the equation of the radius. But they already had it for us. So, now, there's a lot of algebra here now, right? Because now you're supposed to actually find it. So this is something that was a little unusual. A lot of times there's not quite as much algebra, but they went towards maybe a problem or so in there where you've got some of that. So you're going to have to FOIL this out, and you're going to have to do your antiderivative, and then you're going to have to do your right bracket and so forth. And here's what they did. Here's the work they did on that. So there's your pi squared. So they squared it all out. They pulled out the 1/20th, but that'd be squared, so that'd be 1/400th. So they pulled that 1/400th out, then they squared this, and then they did their antiderivative. Then they plugged in their 10, which was a bunch of big numbers. But you could have stopped right here. You wouldn't have had to went all the way to this, okay? But it ends up being that right there, okay? All right. So let's do this last part. Moving along here because we've got some stuff to do. So let's do part C, okay? The funnel contains liquid that is draining from the bottom. Now, that volume problem, that's a good review, even though it's a little different than most of the ones we've been doing. The funnel contains liquid that's draining from the bottom. At the instant when the height of the liquid is 3 inches, the radius of the surface of the liquid is decreasing at a rate of 1/5 inch per second. At this instant, what's the rate of change of the height with respect to time? Well, this should sound familiar, right? All this kind of stuff. So tell me what they say. H is 3. Okay, got it. The radius is decreasing at a rate of 1/5. What are you going to write for that? R prime equals -1/5 because it's decreasing. At this instant, what is the rate of change of the height? So they're looking for H prime. We need an equation that's got R and H in it. Do we have such a thing? Aha, right here. So what are we going to do with that? Do what? Rearrange maybe. Well, do we have to solve for H? But can't we just do the derivative now? When we did these problems, remember, it was implicit differentiation, right? We're doing the derivative with respect to time. So we can just do the derivative right now. R prime is equal to, the 1/20th is just going to set there. And then, what's the derivative of 3 plus H squared? The 3 is 0. And then it's what? 2H, H prime. Right? Remember that? So there's no need to solve for H, because that would get messy. There'd be a square root. There'd be all that stuff. We don't want any of that. And look what we got. What are we going to put for R prime? -1/5, 1/20th, 2, what's H? 3, H prime. So that's like -1/5. Over here we got what, 6/20ths? What's 6/20ths? 3/10. Multiply by 10/3. We got -10/15, which is what, -2/3. Did I do that right? -10/15, multiply across. Negative 2/15 would be negative 2/3. So the rate of change of the height with respect to time is negative 2/3. Let's see how negative 2/3 inch per second, which would have been good. It doesn't look like they gave a point for units, but you should have it on there. You got 2 points for your chain rule. You got 2 points if you did the R prime equals 1/20th 2HH prime. They put DHDT, that's fine. But you got 2 points for that. So if you made a mistake anywhere, it'd be -1. If you made 2 mistakes, you would take those points. Okay, all right. Good review, good stuff. But I wanted to look at that volume point. All right. So now let's go to your 2011 packet that you had for today, and let's go to number 5, because I'm guessing you might have had some questions on number 5. Okay, especially part C, because we haven't learned that yet, but we're going to today. So let's go through it though. Differential equations. So we're going to want to focus on that here a little bit, because that is kind of the thing we've left to the end here a little bit. Of course, we've done some slope fields, we've done stuff like that. But anyway, at the beginning of 2010, landfill contained 1,400 tons of solid waste. Okay, the increasing function W models the total amount of solid waste stored at the landfill. Okay, so that's tons. So W is in tons. It's important to know your units in these problems. Okay, planners estimate that W will satisfy the differential equation dW dt for the next 20 years. So W prime is going to be tons per year, right? W prime will be tons per year. That's over the next 20 years. W is measured in tons. Okay, it says it right there. And T is measured from the start of 2010. Okay, use a line tangent to the graph of W, T equals 0, approximate the amount of solid waste that the landfill contains at the end of the first 3 months, which would be T equals 1/4, right? The fourth. Okay, so we've talked about this. If you have an equation, if you have a line right here, you can do the tangent line there, and there's a point really close. If you're looking for this point on the curve right here, you could find the point on the line, and it'll be really close to the point on the curve. Okay, so we're going to do the tangent line at 0. Well, what do we need for a tangent line at 0? We need W of 0, and we need W prime of 0, right? We need those 2 things. Well, what's W of 0? 1,400. What's W prime of 0? We got to come over to here, right? But now wait a minute. What are we going to plug right here? Not 0, right? That's your W. Well, when T is 0, W is 1,400. So 1,400, is this a calculator one or no calculator? No calculator. So 1,400 minus 300 is 1,100. And then it's 1/25, so it's 1,100 over 25. What's 1,100 over 25? Might be nice to simplify that. 44. I think you're right. 25 goes into 100 4 times, and there's 1,100, so 11 times 4, so that would be 44. Okay, so that's 44. So our tangent line is y equals, it actually be W equals, no, what goes here? The slope, right? 44 times T minus 0 plus 1,400, right? You take your point, which is right here, you take your slope, right? You got that. Now, we're supposed to use that to check when T is 1/4. So let's put a 1/4 in here. What's 44 times 1/4? 11 plus 1,400. So 3 months in, there's 1,411 tons of waste at the landfill. Okay, so it's gained 11 tons. Okay, that's an estimate. All right, moving on. What is D2W over DT2? What's that mean? Huh? W prime, right? W double prime. I'm sorry, W double prime. Okay? So that means we got to do the derivative of this, right? But we're going to have to do implicit differentiation. So we're going to go, so W prime, this is W prime right here. So W double prime would be the 1/25th will just hang out. And then what's the derivative of W? W prime, oh, and the 300 just goes away, right? Oh, that's easy. But then, what do we put in place of W prime? We would put this right here, right? This is W prime right here. So W double prime is going to be 1/25 times 1/25 times W minus 300. Okay, just like that. Okay, so actually you can just take the 1/25 times 1/25, and that's like 1/625, W minus 300. Okay, that's W double prime. Now, it says to determine whether your answer in part A is an underestimate or an overestimate of the amount the solid waste contains at T equals 1/4. Okay, here's where you got to understand this again. Remember what we just found in this problem up here? We found this value right here that was on the line. Is that over or under estimate there? The line is over. Why? Because it's concave down. This is the part you got to understand. You got to say, okay, what's going to make a tangent line be an overestimate? If W is concave down. When do you know W is concave down according to the chart? When W double prime concave down, it'd be negative, right? So what we're going to do here is we're going to put in, at the time T equals 1/4, what are we going to put in for W here? 1411, right? That number we just found here. Well, it's easy to see that's going to be what? Positive. So W double prime is going to be positive. So my tangent line estimate is underestimate. So you're going to say it's an underestimate because, and it probably says, didn't really say to tell why, but we can go, let's see, no, I don't have the answers here right now. But that's why, because it's concave up. All right, now, here we go. Here's the part that we have to learn right now. Find the particular solution. We want to solve this differential equation, which means figure out what W equals, right? This is W prime. Why can't we just do an antiderivative of this? Because there's a W in there. If what was in there, could we do an antiderivative? If that was just T, if it was like X or T, we could just do an antiderivative. We can't. So we don't know how to do this antiderivative. Now it turns out it's like a Newton's law of cooling. This is actually like a Newton's law of cooling, so we can say, hey, this is one we kind of memorized, and we can look at it. How that worked, if you remember, Newton's law of cooling said if you had Y prime equals K times Y minus big T, right? Well, that's what we have here. We have W prime equals K times W minus 300, right? And the solution to that was big T, which in this case would be 300, plus A e to the K, and what's K in this case? 1/25, right? That's actually good. That should be the solution, because it's like a Newton's law of cooling. But we're going to learn how to do that right now. Okay, we're going to learn how to do that right now. So you might, just jot that off to the side. But we're going to come back to this, and we're going to solve this here in just a minute. Okay. So, but this is like a Newton's law of cooling situation. All right. All right. So here we go. So you might go to your notes at this point. Okay. So this is going to be what we call a separable differential equation. A separable differential equation. Now, if you when you get out of Calc 1, 2, and 3, and you take a class called differential equations, you learn about all the different types of differential equations and how to solve them. Kind of like in algebra class, you learn about the different types of algebraic equations. You learn how to solve linear equations in like 8th grade, Algebra 1. Then you learn how to solve quadratic equations, like the quadratic formula and stuff like that. You learn how to solve exponential equations, in Algebra 2. You get into logarithms, stuff like that. You learn how to solve trig equations when you get to advanced math, right? You learn how to solve those kind of equations. So there are different types of equations, and they all have different types of strategies on how to solve. Okay? Well, it's the same thing with differential equations. You have to identify what type of equation you're looking at, and then you apply that strategy. Okay? So simple differential equations, the ones that say y prime equals, and then they have x's, we just do the antiderivative. Okay? Separable differential equations is another type of differential equation. Now, by separable means we can divide and we can separate the x's and the y's. We can separate the inputs and outputs. Here's how this looks. Now, we already know this one too, right? This is the one we memorized also. What's the solution of this one going to be? It's just this right here. No. What's the solution to this? Y equals. So what's this one going to be? Okay. So the solution to this should be that right there. That's what, remember, the solution to a differential equation is the original function, right? The solution to a differential equation is the original function. That's what we should end up with on this problem, okay? Here's how we're going to do it. First of all, we're going to write y prime like this. Now, how did I know to do dt? I didn't. I could have done dx there. That's fine. Could have done dx. This problem, all we can see is the y. We know that's the output variable. Who knows what the input variable is? Might have been x, might have been t. I'm going to use t. Okay, because I kind of know where I'm going with this. But if the problem's got both x's and y's in it, you'll know. If it's got t's and y's, then you'll know. T is the input variable, right? But if it only has the y's, you don't know what the input variable is. So you can choose. You can use t. Now, it might have said, sometimes in the directions it'll say, find the solution y equals f of x. Or it might have said, find the solution y of t. Right? And then you know what the input variable is, because they might have said it in the directions. Okay? All right, so here's what we're going to do. Now, it's a lot like when we did u substitution. We're going to separate the y and the t. And we always do that by doing the same first step. We're going to multiply the dt over to that side. Just like that. We're going to multiply that dt over to that side right there. We've just separated the variables. Okay? Separated them. These are called separable differential equations. Now, they have to get separated by multiplication or division. We can't separate by subtraction because of this division that we have right here. Now, I need to get the y's together, so I can't leave this y on the side with the t's. I need to get the y's on one side, the t's on the other side. Now, the 3 I'll just leave there, because if I move it over, it's 1/3, and I don't want any fractions if I don't have to. So I'm going to move just the y over. Now, sometimes, don't write this, but sometimes people will write this, divide that y over. I'm not going to write it that way because I think that's more confusing. So I'm going to actually write it this way. I'm actually going to, when I divide that y over, I'm going to write it 1 over y and then dy like that. Okay? It's better, in my mind, to do it that way. Constants can be on either side, doesn't matter, but we need the y's with the y's, we need the x's with the x's. Okay? So we never want to divide by the dy. We don't want to dy on the bottom. We never want that, right? So we always multiply the dt over there like this. But we can have y's on the bottom like there. We have to divide that over. Matter of fact, it's fairly common. Then what are we going to do? Well, it's just begging for it. You can just tell this problem is just begging for an integral symbol, isn't it? It's got the dy there. It's got the dt there. It just feels like there ought to be an integral symbol there. What we're going to do is we're going to do the antiderivative of both sides at this point. We're going to do the antiderivative of both sides. The left side with respect to y, the right side with respect to t. What's the antiderivative of 1 over y? ln y. Now, we should put bars around it, but we don't really have to. It's not going to matter in how we solve the problem. Now, normally we would put a plus c here. Normally we'd put a plus c on both sides, but when we go to solve it, we're going to just subtract the c over, and what's c take away c? No. I knew I was going to get you. What's c take away c? Some other c, right? Some arbitrary constant take away some other arbitrary constant is just some arbitrary constant, because we don't know if it's the same arbitrary constant. So c take away c is just some c. So I'm not going to do a c on this side. I'll do the c on the other side. What's the antiderivative of 3? not 3x, 3t plus c, okay? All right, now, I should let myself some room here. All right, so, now, that's all for y, right? Because that's what I'm trying to do. I'm trying to solve this differential equation, so I'm trying to get y equals, right? I'm trying to get y equals here. So I need to solve for y. How do I solve for y? How do I solve an ln here? Yeah, what do I do? I don't take the natural log. I don't take the natural log. I already got a natural log. No. All right, let's review this. All right. Now, how can I do that as a log? That'd be log. These 3. Okay, so now tell me how I go to that. This raised to that equals that, right? Okay, back to this. So what do I do here? E raised to the 3t plus c equals 1, right? That's what I'm trying to do. That's what I'm trying to do. Now, this is going to be fairly common because you do get LNs a lot in these. Matter of fact, you get them so often that people mistakenly, students will get LN every time they do one of these. And you don't have LN every single time. And I'll show you some examples of when you don't. But sometimes you do. If you have a y here, you divide by y, you're going to have a 1 over y. That's going to be an LN. Okay, now, you look at that and you say, wait a minute. I thought we said the answer was going to be that. Well, it is kind of. Let me show you here. 3t plus c, what can we do with that? Well, we can do a little algebra trick to this. Everybody look at that. You buy that? Is that right? When you multiply, you add the powers, right? So if we got powers that are added, we could break it apart like that. Now what's e to the c? Just some constant, right? So we could call that big C, and then I can move it in front. Or I could call it A, right? I could call it big A if I want. And sure enough, that's what I got. So whenever you have this ln and you have that plus c in there, right? You have to make sure you do the plus c at the right time when you do the antiderivative. But whenever we have that plus c on an exponent, a lot of times we split it apart like that and we make it. And that's how come we ended up with that a on here. It wasn't a plus c, but it did come from a plus c. And sure enough, we just figured out how we could do this one that we memorized before. And we know why it ended up being an e. It was because the ln in the antiderivative. Okay, so now let's go back to the one we were just working on. So go back to your packet, and let's go back to this one right here. So we're supposed to solve this differential equation. Right? So we're supposed to solve this differential equation. And it's got a w, so we want to get w equals, right? So what do we need to do? We need to separate the variables. So I would do it one step at a time. It's up to you. I would just first move the dt over there. But it depends how comfortable you are with your algebra. Right? Depends how comfortable you are with your algebra here. Now, what do we need to get over on the w side? This whole thing. We can't split out that w, right? There's no way we can get that w itself out of there. So the w minus 300 is going to have to stay as a thing. Okay? So I'm going to divide that over. I'm not going to be able to get that by itself. Okay? So I'm going to, the 125th I can leave here on this side here. Okay? But the w minus 300 is going to have to stay together. Okay? Now, hang on a second. Before we go any further, let's talk about what we can separate and what we can't separate. Your book has some examples. If I have this, okay, right there, could I separate those? Could I get the y's together on one side and the x's on the other? Tell me how. If I move the dx over there, right? Now tell me what I would do to get that y out of there. Can't do it. Can't do it. I can't divide this over here because the x got to come with it. I can't just divide the y because the dx has got to be times this whole thing. I can't distribute this. Never in any of these problems do we ever distribute that because now we got two dx's and we got those together, but now we got that. How are we going to get that apart? You're not going to. This is not separable. Usually when there's plus signs in there, they're not separable. Now, if that would have been a constant, that's a different deal. If this would have been 3 plus y here, okay, like that, now I could multiply the dx over to the other side, like this, and then what? Divide by the 3 plus y, right? Oops. And now I'm good, right? And now I could do my integral, and that'd be an ln, right? And we'd have that kind of thing, right? So, understand the difference, right? The 3 plus y I can treat as one thing, and I can divide it over, and that's fine. And now I got y's on this side, x's on this side, even though it's only 1, but still, that's fine. Constants can be on either side. Okay, so some things are not separable. Some things are not separable. Now, I'm not going to give you any of those, but in the book, there might be some homework that says, you know, is it separable, yes or no, or something like that. So you got to understand that sometimes they're separable, sometimes they're not. But they're going to be separable by dividing and multiplying on both sides, not by subtracting, because that doesn't work. Okay, so back to this. So now we can do the integral of each of those, right? Now what's the integral of this one right here? ln w minus 300, we put the bars, but we don't really need them, it doesn't really matter, here, equals, I'm not going to put a plus c on that one, I'm going to wait and put the plus c on the other side. What's the antiderivative of 125th? 125th t plus c, right? So you can see this is going to be very much like the other one we did. How do we get rid of this ln? So we got w minus 300 would equal e to the 125th t plus c. That's all up there, right? Now what are we going to do with that plus c up there? Split it apart, right? Split it apart like this, and then it'll just be a c out in front, right? It ends up being just a c out in front. So it's going to be w minus 300 equals a c out in front, e to the 125th t. And then we add the 300 over. And isn't that what we just said a minute ago it was going to be? Except we had an a in there. Isn't that what we just wrote down a little bit ago? That we said was going to be the solution? But we're not done yet. Why aren't we done? We have an initial condition to plug into there so we can get the c. So we can plug our 1400 in. So we got 1400 equals 300 plus c e to the 125th times 0. E to the 0 is 1, so c is going to be what, 1100? So the w is 300 plus 1100 e to the 125th t. And is that all they wanted on that one? Was the solution? They just wanted the solution. Now what they sometimes will do is ask you to compare that to what you did up here, right? So we could plug in a value, we could plug in a 1/4 now, we could plug in a 1/4 into that, and we could compare it to our answer in part A, right? We could plug a 1/4 right there, and we could double check our answer to see how close we came. That 1411, right? But this is a no calculator. That is solving a differential equation, getting the w by separating the variables. Now, let's do, so we don't think that we're always going to be getting, ln's in our problem. Let's do this one right here in your notes. Let's do this one in your notes. I don't want you to think you're always going to have an ln kind of a situation. That's only when you have 1 over y to the first power, 1 over y to the first. You might have different kinds of y's. Okay, you might have different kinds of y's. So what are we going to do on this one to separate? So you're going to times by the dx. Now you're going to get good enough here at some point you can just do 2 steps at once. Like right here, you can, well, I'm going to divide by e to the y. So I'm going to have 1 over e to the y, right? And on this side, I'm going to have 3x squared minus 6x dx, right? And I can put parentheses around that, right? I mean, I understand that's there. And then I'm going to throw them in my integral symbol, right? So once I get those separated, I throw on the integral symbol, which is basically telling me, okay, now do the antiderivative. Now do the antiderivative, right? So the antiderivative, what's the antiderivative of 1 over e to the y? That doesn't have ln. It doesn't have anything to do with ln. Remember, the only time we have ln is 1 over u du. And then that's ln u plus c, right? That's the only time we have that. What is that? That's the same as e to the negative y, right? What's the antiderivative of e to the negative y? It's got to have a negative on it, right? Because you're going to kick out that negative, right? So it's negative e to the negative y. We won't put the plus c on that side. We'll do the plus c on this other side. So, right, you got to know your antiderivative, right? It's not an ln all the time. Just because you have 1 over something doesn't make it an ln. What's the antiderivative of 1 over x squared? Is that ln of x squared? No. You make that x to the negative 2 and you do your power. Right? So we got to make sure we understand it. All right. So what is the antiderivative of 3x squared? X cubed minus 3x squared, raise it up to a 2, divide by 2, plus c. Now, let's get rid of that negative first. So that'd be negative x cubed plus 3x squared. Now, do we need to change that to minus c? We don't really have to, no. Okay, let's do that. Then what? Do the natural log of both sides. That would leave you up. Negative y equals ln like that, and then put the negative on the other side. Now, for the general solution, you would be done. But there's an initial condition, right? If they say solve the IVP, right? IVP means initial value problem. So that means that you throw in your initial condition. If it's just the general, so that would be a particular solution. The particular solution is the one where you plug in and get your C. The general solution would be that right there. So let's put a 1 in. So we get negative 1 plus 3 is what? 2 plus C. So we got, and that's going to be 0. So we got negative ln 2 plus C. Correct? Now how do we solve something like that? Be e to the 0, which is just 1, but e to the 0 equals, well, we could get rid of the negative. We could divide by negative, right? And that's still 0, right? And so e to the 0 equals 2 plus c, and that's a 1. So c is negative 1. All right, so final answer, y equals negative ln, negative x cubed, plus 3x squared, minus 1. Right? Just like that. Okay? Final answer. All right, so solving a differential equation that is separable. Okay? Now, let's go back to our packet. I think I wanted to do, let me see, did we go back to 2016? No, I don't want to do the one in 2016 because I think that's like one in our practice. Oh, no, it's not either. Yeah, this is a good one. Okay? This is a good one right here. 2016, number 4. Okay, have you done this one yet? Okay, now we're not going to take the time to finish it right now, but slope field, You got plots and points, right? You got plots and points, and do that. Let y equal a particular solution, and they give you initial condition, write the tangent line. We already did that earlier. And then it says use that equation to approximate 2.1, right? Same thing we did a little bit ago. So you're gonna write your tangent line. You need your slope, well, you got your y prime equation, and you need your point, which you got right there. You got point, slope, write your tangent line equation, plug it in 2.1, away you go. So let's focus on part C. Part C says find the particular solution y equals f of x to the given differential equation with the initial condition f of 2 equals 3. Okay, so here it is right here. Okay, you guys try. Here's your differential equation right here. And let's separate that. It says find the, it's the only method that we're going to learn of solving differential equations. So every problem in your packets, it says find the solution to the differential equation. Unless it's a straight antiderivative, if it's got a mixture of x and y, it's going to be separable. You're going to be able to separate. Okay, go. Don't look up here. Just one sheet. All right, how did I do? So what are you going to do? You got to get this y over here, so 1 over y squared. You got to get the dx over here, so that's going to stay on the bottom. That's going to be 1 over x minus 1. That's 1 over y squared. That is not an ln, right? 1 over y squared is not an ln. That's y to the negative 2. So the antiderivative, you raise that up 1, it'd be negative 1.
divide by -1, which would be that. The antiderivative of this is an ln. This is ln x minus 1 plus the c. I multiplied the negative over, got it there. Now, I got 1 over y. How do I solve that? Well, basically y here and divide, right? It just, if that's 1 over y, then that's just 1 over. Now, I went ahead and put the negative up there, and you might say, well, what about this negative thing? But that would just be, if I take out a negative, that make it minus c, so that part doesn't matter, right? The minus c, so whatever. So negative, I put that on top. But I could have left it down here. That's fine. I could have left it down there on that. That's okay. So it doesn't really matter, but I moved it up. And then I found the c, so I put a 2 in here for x. 2 minus 1, ln of 1 is 0. 0 plus c, so I get -1 over c equals 3. So I get c equals -1/3. So I could have stopped right here, too. That would have been fine. You could have stopped right here, right? The negative could have been down there. Could have stopped right there, but I thought I don't like that 1/3, so I took the top bottom times 3. So I took the top times 3, took the bottom times 3, and I got that right there. Questions about that? Just a bunch of algebra. You probably could have, it says find the particular solution y equals. So I have seen some problems where they don't say y equals. They say just find the particular solution in terms of x and y, whatever. So sometimes once you get like to here, you can almost stop, right? You could plug in your 2 and 3 right now. You can put your 3 there, your 2 there, right? I mean, but usually you want to get y equals. So usually once you do your antiderivatives and you get to this line, then you're trying to get y by itself. And then it's just a matter of moving stuff around, some trig, some algebra, whatever. Okay? All right, let's double check that. Let me see here. 2,000. Do I have that up here? I think it would be already. What number was that? Number 4? Right here. Now look what they had. See, they had it the other way around. Look what they did, though. See, when they got right here, they went ahead and plugged in their initial condition. Like I said, they didn't get the y by itself till later. Now look what they have. Theirs is a little backwards from mine. I had a negative up here. And then so that would have made this positive and that negative. Same thing. But then they said, so look what you got. You got like 5 points for this. Separating the variables. So step 1, right there, you got a point. Your antiderivatives, you got 1 point for doing that antiderivative. You got 1 point for doing that antiderivative. Having your constant of integration and putting in your initial condition. So making sure you have plus c and plugging that in. You got 1, and then you got finally 1 for getting the y by itself. So if you can get that other stuff, and you just don't get the y by itself properly, you can get 4 out of the 5 points. Okay? If you didn't put the plus c, the most you can get is 3. You can't get these last 2 if you didn't use a plus c. And if you didn't separate variables, if you just tried doing like a straight antiderivative or something, you can't get any points. Okay? All right, so that's separation variables. Okay, so got some work time here, the 7.4 line on your worksheet here. There's just a handful of them in your book. So practicing this, separating the variables, getting the y's on one side, x's on the other, multiplying, dividing. Don't think you're going to have an ln every single time. If it's x to the first power or y to the first power underneath, 1 over y or 1 over x, then it's an ln. Otherwise, it's just a negative power, it's an antiderivative.